Right, welcome back. And of course, we have theory, we know what we want to measure, we create detectors, we're learning a lot about detectors, but the electron ion collider also an accelerator. So we're going to learn today from Sergei Nagaitsev, technical director of the electron ion collider, is the accelerator part.
Hello. So my name is Sergei Nagaitsev. And I'm working at Brookhaven National Lab. But I also have an appointment with Old Dominion University in Virginia, which is next to Jefferson Lab. And I came from Jefferson Lab a little more than 1 year ago to start in this role. Before that, I was for a long time at Fermilab. Has anyone heard here about Fermilab? Okay, good. So I was there responsible for many elements of the Tevatron collider. And then after the Tevatron collider was shut down in 2011, I was responsible for delivering muon beams for the muon G-2 experiment. If you ever heard of the G-2 experiment, I've been responsible for delivering beams, proton beams for the neutrino oscillation experiment called NOVA. So now I'm at Brookhaven. And today we are talking about something much more simple than nuclear theory. In fact, most of the discussions we are going to have today are based on purely classical equations of motion. There are some quantum effects in accelerators that mostly have to do with synchrotron radiation, but overall we are going back to classical physics. Of course, it's highly relativistic, but still classical physics mechanics. Okay, so I am here to talk to you about the very basic things about accelerators, and I'm going to be using a little bit of a blackboard, and I'll show to you how to build an accelerator. It turns out in 3 easy steps at the end. But before that, I just wanted to introduce to you that there's, let's see, how does this work? Okay, yeah. So the electron ion collider will be built at Brookhaven in the existing tunnel, which one would ask, why would you want to reuse the tunnel? Well, because tunnels are expensive. This is a 4-kilometer long tunnel built underground in order to create radiation shielded environment. So the tunnel cross section looks here. It's a fairly easy construction. You dig a trench in the circle, you pour concrete floor, and then you install the hoops made of steel, and then cover it back up to create the berm, and there you go, you get yourself a tunnel. So that's of course there are various elements of the tunnel and various other things that we need in the tunnel, like water, compressed gas, liquid helium, fire sprinklers, cables, many other things, but that's basically what it looks like. And I'm showing a cross section of what it's going to look like in the area that we are calling a 41 GeV arc. So in the 41 GeV arc, which is here, you can see that we have 4 beam lines, if you will, which I'll explain to you what the beam line is in a moment. But you can see that we have a ring in the corner here. That's a synchrotron to accelerate electrons. There are 2 lines to store ions or protons. And then there is another accelerator or storage ring shown here in blue and right here. And that's to store electrons. Okay, those rings intersect in several places, but really the beam collide only in two places. There is a primary detector location, and then there is a future detector location where these beam lines truly intersect. Everywhere else, the line, even though they intersect in these two places, we actually position the electron ring slightly tilted so that the plane of the electron ring is off horizontal by a little bit, so that we miss the vacuum chamber intersection in these two places. So the electron ring is slightly above, rotating in the plane not parallel to the main ring, to the hadron ring. Okay, that's what it looks like schematically. Of course, I wanted to advertise a little bit for you if you want to read more about accelerators. Turns out that pretty much all we know about nuclear physics, particle physics, elementary particle physics comes from accelerators. Of course, recently we are learning a lot about particle physics by studying cosmology also, but the majority of our knowledge comes from particle accelerators, and those are truly the engines of discovery. In fact, we've looked at how is Nobel Prize, which I'm sure each one of you here is trying to work on right now, thinking about it, how often a Nobel Prize is awarded based on work directly influenced by accelerators. And it turns out that every 3 years, on average, a Nobel Prize is directly associated with or influenced by an accelerator. This is data. I didn't make this up. These are all, go and read. It's a little bit out of date now. There is more data since 2011. But you can see that on average, of course, it's not just particle and nuclear physics. Now we have a proliferation of various applications of accelerators in science, including biology. The most recent example of accelerators have been used to help with development of a COVID vaccine. Just recently, it was done at Argonne, which is the national lab, a sister lab to Brookhaven. Argonne National Lab has a very famous electron storage ring to produce synchrotron radiation that studies the structure of proteins. Okay, so and viruses, for example. Okay, so right near us, of course, at Stony Brook, there are 3 great accelerators, which are in the DOE language called the users' facilities. Okay, so many accelerators have users, but DOE, the Department of Energy that funds our research at Brookhaven, designates a particular type of facility to be a user's facility, a national user's facility. And at Brookhaven, we have 3 such facilities. And one of them is, of course, called RIG, the Relativistic Heavy Ion Collider, which will end its operation at the end of 2025. And at this point, we will start taking the hardware out of the tunnel and start replacing it with hardware for the electron ion collider. Other 2 facilities, we're not going to talk about this. One has to do with testing, with doing accelerator R&D, research and development for novel accelerators. That's this test facility. And then there is another facility called the National Synchrotron Light Source, which is it's kind of a sophisticated X-ray machine that helps people study materials, biological samples, various other, material science. Okay. So why accelerators are such interesting tools. And I think the reason is that the accelerators are really instruments for providing highly directed forms of energy. Okay, so this this is an ensemble of particles, whether stable or unstable. It could be unstable, like in the case of muons, or if because of the relativistic boost, muons can survive in at high energy for quite a while. But the basic reason why accelerators are so important for us as scientists is because they provide you with the probe that has a very highly directed form of energy. So you can use this energy at your choosing. The more effective, the better. So you don't want to waste it. But in general, the number of particles that we can provide in accelerators is from one single electron. So we work with single particles sometimes. I've seen myself single electrons in the ring because they produce light, and with your own eye you can observe a single electron circulating in the ring. Somewhere I have a video of that even, and up to 10 to the 14 particles, which is the state of the art. Facilities like the spallation neutron source is very hungry for protons. They provide 10 to the 14, or if you've ever heard of the future muon collider, those machines will need to have high intensity proton beams per bunch, 10 to the 14 per one group of particles. So the basic technologies that we use in accelerators come in two flavors. You either use something to bend and focus the particles, or which is magnets of various shapes, magnetic fields, static magnetic fields, or you use sophisticated accelerating structures such as copper cavities or niobium cavities. Niobium cavities are used because niobium can be superconducting at low temperatures, like 2 Kelvin. Magnets are made of niobium tin, niobium titanium alloys that also become superconductive and therefore can provide much higher field. Do you know what an MRI solenoid is? Magnetic resonance imaging. You've seen huge solenoids in hospitals where you can stick your head in. Okay, those are made of superconducting wire, and this wire was developed by Fermilab in the 90s. Okay, the entire MRI technology, making the solenoids, was a spin-off from the Tevatron collider that was built at Fermilab in the late 80s, beginning of 90s. Okay, so let's move on for a second. So colliders. So we eventually, I'm slowly going towards the electron ion collider. So colliders allow for us to use the energy stored, provided by these beams very effectively, because if the beams are symmetric, then of course their entire energy is available for new particles, for the production of new particles. For a symmetric collider, then the center of mass energy is twice the energy of two beams. For an asymmetric collider that we are building, as the electron ion collider, it's roughly twice the square root of the product. Okay. Since its inception, this idea appeared, I believe, in the early 1960s. The first collider was the Princeton Columbia collider. I forgot where it was built, but it's not far from New York, somewhere here. And since then, 31 colliders were built, many of them decommissioned. 7 are in operation today, including 1 in the US, 1 in Europe, 2 in Europe, sorry, Daphne and LHD, Bepsi in Beijing, Super Cake B in Japan. 2 last ones are in Russia, and 2 under construction. The Electron 9 collider and in here at Brookhaven and Nika in near Moscow. Okay, so this is the landscape of colliders. And by the way, just recently, CERN and the United States Department of Energy have agreed to collaborate on the next study for the so-called Future Collider, FCC-EE. If you've ever heard of this, this is the next collider that's under study. It's not yet being constructed. We are just thinking about it, how to build it. Because as you will see, it's quite expensive to build colliders. So how did we get to the Electron 9 collider? It turns out it took now 20 years for the community to build the physics case and to understand what is it that we want to study. Starting in 2002, we gradually developed the understanding of what is the parameters we want. How many particles we want per beam, what energies we want, what ions, what this and that. Finally, the community in 2015 came together and created a very important for us report, which was a long-range plan for the community, which you are now joining, some of you. So pay attention how this is done. It takes many years to create, and from idea to where we are today, and we are not yet even constructing the machine. We are still in the process of trying to get funded. Okay, so but we are in the final stretch. Believe me, we are now converging on the final machine configuration that should convince the funding agency and everyone else to give us roughly $3 billion to construct the machine. Okay, so when the Department of Energy agrees that the machine is needed, they write a statement. And my entire life now is driven by these 4 lines. This is what I'm constructing for you guys at Brookhaven. It's all written in these 4 lines. That's all I get from the Department of Energy to construct the machine. They tell me, look at the 2015 long-range plan. Right there, that's the piece of paper that I have to look at. They also tell me that, oh, by the way, the beams have to be polarized up to 70% polarization, which you will learn tomorrow about from my colleague, Christoph Montag. Will come and talk to you about more sophisticated, but today I'm just painting for you a very simple picture of how things are done. They tell me, okay, you need to provide 70% of the polarized beam for electrons and light ions. However you interpret it, maybe it's deuterium is a light ion, or helium, also a light ion. But perhaps that's where we stop. I don't know where, how far we're going to go with polarized, but certainly protons and polarized deuterium. Then they tell me you have to be able to switch from protons to the heaviest elements, nuclei, fully stripped. So make sure that I don't store ions with electrons. There has to be fully stripped ions. Variable center of mass energy, and here are some examples of where what type of we are. These are 4 sample points from 28 GeV center of mass 240 GeV center of mass. This is the range that we are providing, upgradable, high luminosity, 10 to 33, 10 to 04, and possibly one more interaction vision. Okay, that's all I get. So now, of course, just one slide for you to understand how the projects are constructed in the US. These 4 lines are all in this document called mission need statement. This is where the DOE agrees that yes, for our mission of the US executive branch of the government, which they belong to the executive branch of the government, the DOE, for their mission, it is absolutely critical that we construct the electron ion collider with these properties. And then from then on, we start developing the machine. We have the tunnel. That's good. We have some interest. We have power. We have water. We have sewer. We have gas. And all of this comes together eventually. And it comes together at the point which is called execution. Okay, so we are now approximately here, but we have not yet gotten an approval from the Congress that it will eventually require for the Congress to put it in their annual bill and the annual budget and say, okay, guys, here is the will of the people. We, the people of the United States, are giving, through Congress, giving you $3 billion to construct the project. We are not there yet. We are still before that. And soon, perhaps at the end of 2025, we will arrive at the point where the design is complete and the Department of Energy and other countries that now joined us. The UK has given us 100 million already. France is on the verge of giving us some funding. Italy, Japan, Korea. So, maybe I'm missing some, but we are talking actively to other Germany, so there is a number of countries that are willing to stand up. Even CERN is willing to, because they are also thinking how to diversify. They don't know whether they can afford FCC or not. So, the CERN has to be thinking, what's after the LHC? Where can our scientists that are now working at an ALICE detector, which is a nuclear physics detector, LHC, where are they going to go? Well, they're going to go here because we are the only game in town now, right? So this is where the action is going to be in 10 years after we construct the electron ion collider. But we are not quite there yet. The most important part for me is to bring the project design to completion where the DOE agrees that yes, you have a good design, technical, and yes, you can start the construction. And here is the check. Okay, so you are with me so far. I hope it's interesting to you to explain how this works. But this is a multi-year, it took us 10 years to develop the physics case. And we are now, let's say, 8 years away from the first beam, approximately. Okay? Any questions? You guys tired? It's interesting, isn't it? Yes.
What does the percentage of polarization mean? Is that just the percent of particles that are successfully polarized, or?
Well, the definition of polarization is, let's say, polarization, the number of particles with polarization up minus polarization down divided by the sum. Yeah. So, okay. Okay, so let's go now talk about a little bit about physics finally. So the IC requirements then are formulated in a more technical table for me. You know, and some of them are quite unique. No one has ever done this before in other colliders. So we have to be really careful about how to design and build this machine. So there is the so-called high luminosity, which we will talk about in a moment. Polarization, very quite unique for both beams. No one has ever done this before. So Hera, the previous, do you know that there were two electron ion colliders before this one already? One in Japan called Tristan, and the second one in Hamburg called Hera. And so, of course, each one of them had their own physics cases. Each one had high hopes that they were gonna do the physics that we and not quite succeeded. So now we are, you know, the third time is the charm. You know, we are trying to learn from the two machines in Japan and Germany and add more sophisticated elements to it so that finally we can look at why does proton have spin and what is the origin of mass for protons. So these are the two key questions. Of course, there are others, gluon saturation, but these are the two physics questions that still remain unanswered by the community of nuclear physicists. What is the origin of spin? And that's why I need polarized beams. And what is the origin of mass? That's why I need super high luminosity, because we're going to do a tomography of using an elementary, particle and electron as a probe and proton as an object. We're going to shine electrons right through it and detect their scattering, and then try to reconstruct a 3D image of a proton. I'm simplifying it, of course, because it's actually not an image, because it's a Fourier transform. But whatever you studied today or earlier, various. But that's where I'm going with this. Okay. So what's my goal for today? So if you open the conceptual design report for the electron ion collider, you'll notice that the very first, well, actually it's table 3.3, but for me it's actually table number 1 that has all these parameters: species, energy, center of mass, energy, bunch intensity, number of bunches, beam current, RMS, normalized emittance, RMS emittance, beta star, IT, RMS beam size, blah, 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 all of these things. So my goal today for you is, like how when you go to buy stocks on the, New York Stock Exchange, you have to learn various terms of like, what is the price to earning ratio? What is all of this? There is a table that comes, but so here, same way, I'd like for us to talk about a couple of things that I'm highlighting, and eventually at the bottom is the number that is really important. That's the luminosity. Okay. Right, 10 to the 34 per centimeter squared per second. What does it mean? What does the luminosity number mean? What does it signify? Think about the units. So 10 to the 34 per centimeter squared per second.
The dance of particles? I mean, the dance of the particles?
The dance?
The dance in
The density of particles?
yeah.
No. So let me first. So think about it. Yes, I am a little bit. So let me. So for today's plan, so let me start by first explaining to you where the particles come from. right? So we want to get particles. When then we need to know how to accelerate them. We talk about luminosity, the beam transport, beam size, and maybe beam stability. So these are the very simple questions that I wanted to discuss with you today from an accelerator standpoint. So how do you build a particle accelerator? Well, there's 3 easy steps. You need particles, you need add acceleration and add focusing. And eventually you need to add collisions if you want a collider. So these are the simple 3 steps, and that's what I'm going to talk about today. So first, the energy discussion. Well, yeah, let's go back for a second to the luminosity. Where is my luminosity? Yeah, okay. So I'll get back to the luminosity in a moment. It looks like I'm a little bit out of order. So so the very first accelerator that was built was the electrostatic accelerator. Like you take a battery and you charge one plate compared to another. If you are able to find free electrons, you emit an electron, and the electron is accelerated from a cathode to the anode, gaining a potential difference and of some few electron volts, and therefore we measure energy in electron volts. Okay, so the very first application for nuclear physics was, of course, the Harcroft and Walton experiment, where they took high energy protons and produced the first nuclear reactor on an ion of lithium, producing 2 helium nuclei. Protons come from something called an ion source, which starts with a highly ionized plasma, and then using a potential gap or some kind of a battery, if you will, right here, you can see, some kind of battery applied here, you extract positive ions from plasma, and you then can accelerate them further. For electrons, you can boil electrons off from the cathode by heating it up to very high temperature, let's say 1000 degrees. Then some of the electrons can, at the tails of the Gaussian distribution, can escape with because the energy at 1000 keV is 0.1 electron volts, and maybe some tunneling allows for electrons to escape, and that's how you produce free electrons to accelerate. Okay. So those particles can be then accelerated using electrostatic accelerators. And this type of acceleration is called the potential drop acceleration. This is a photograph from Fermilab. This is what used to be in the beginning of all the, this is the very first machine, very first accelerator that accelerated protons using the same principle as the Harcroft and Walton generator. I'll say it in a few words, but then there was also a machine called Van de Graaff. I don't know if you took physics in undergraduate or graduate, you saw this belt machine, and it's a demonstration that using a plastic belt, you can charge up the high voltage terminal, and the highest machines probably are 20 megavolts, producing 20 MeV particles at most. So that's the highest energy that you can provide with an electrostatic machine, about 20 MeV. Of course, it's not enough for many of the studies, especially high high energy elementary particle physics. And now it starts at the T1 TeV range. So how do we get to TeVs? Well, the first principle came from the understanding that particle circulating in a uniform magnetic field, its frequency very weakly until gamma is until the particle is not, while particle is non-relativistic, so gamma is close to being 1. You can see that this cyclotron frequency, or also called Larmor frequency in the uniform field, weakly depends on particle energy. Therefore, it doesn't depend on radius as well. So particle oscillates at any radius with the same frequency. This, of course, led to the invention of a cyclotron, in which you take a uniform magnetic field produced by two poles of a magnet, then cut it in half, split it, and then apply electric field using a radio frequency generator that allows for particle to be accelerated only when the phase of the field is correct. So the recipe is that you take the magnetic field to bend the particle around, and then sinusoidally varying electric field in between these two halves allows for particles to keep being accelerated at every turn. So this was the first cyclotron built in 1931 with 1 kilovolt gap. So on each turn, a particle gains 1 keV. And if you count, maybe there are, 10 turns. So in the handheld cyclotron, people were able to produce 80 keV protons. So this was the first prototype that was built at Berkeley. And of course, these were the first 2 Nobel Prizes that were awarded based on particle accelerators technologies. The first one is Ernst Lawrence, and the second one was for Cockcroft and Walton for the splitting of lithium nuclei using a proton from a high voltage generator. Okay, so this now still is not enough for us to get to the electron-9 collider. So an electron-9 collider, just like any other modern accelerator, employs similar to principle to cyclotrons. We use the revolution frequency of a particle around the ring in order to bring the particle to the device that's called an RF cavity with just the right phase, so that it sees an accelerating field as it passes through this cavity. In any other time, the field can be varying, but when I bring it so if my RF frequency in this cavity is a harmonic of the revolution frequency, then I can phase and the revolution frequency is determined by the path length and the velocity. I can bring this particle to this cavity with just the right phase of the field, so that I see the maximum accelerating field through this cavity. But this can also be done by unfurling this circular principle into a linear machine, and that's called a LINAC. So if you look at, so let's now talk about some simple beam property that you will encounter often if you interact with people like me, called beam rigidity. Does anyone know what this is? Literally, it means how rigid the beam is. The more the more energy the beam has, the more rigid the beam is, and it actually is quite. Let's make sure that I am following my notes. So we remember we said that the site, yeah, I'm gonna erase this. Remember, we said that the cyclotron frequency omega c, which by definition is, of course, v naught particle velocity divided by the radius of the trajectory. We said that this is q v naught divided by gamma MC. Okay, I like using Gaussian units. You know why? You guys like Gaussian units? Who is a fan of Gaussian units? Oh, we are a minority here. What are you a fan of them? What are you guys? Okay, so I like Gaussian units because A, I remember him. I can never remember any of these mu naughts. B, the electric field and magnetic field have the same units. Gauss, that's called Gauss. For Gauss, it's very simple to remember. Right, and then you convert it, everything using whatever your favorite way to convert it, using classical electron classical radius or some. But one thing is good to remember is that one Gauss equals 300 volts per centimeter. All right, because the electric field and magnetic field have the same units. That's the only number I have to remember. One Gauss equals 300 volts per centimeter. All right. Okay, so because my cyclotron frequency is okay, so here this is so because this is my definition of the cyclotron frequency, I can manipulate this a little bit. And I can say B naught times R, the radius of the band of the spiral, equals to V naught, which is gamma C or beta C. So I get 1 over Q times beta gamma and C squared. All right, which of course is PC over Q. So that's if you then convert to units, this is what you get. So okay, how do we use this? How do we actually use this rigidity? So what is the beta rho or BR is called the beam rigidity. So let's say that we are interested in knowing what is the magnetic field needed for the LHC beam at 7 TeV. Okay. So for 7 TeV, my rigidity is 2.3 times 10 to the 4 Tesla meters. I'm using not my favorite units, but so that because I'm just trying to be nice to you. So let's keep it 2.3 to the 4 Tesla meters. That's the beam rigidity. So now I can tell you that the dipoles at the LHC are 15 meter long. These are the dipole magnet. Each one is 15 meter long. And the number of dipoles is 1276. where am I going with this? So, LHC beam makes a complete circle circumference, which equals to 2 pi r, we know, equals to the number of dipoles times the length. So that's what it takes for the LHC beam to complete one circle. So each, in each dipole, you have a portion of a circle, and then maybe a straight line. So, okay, so what does it mean? Well, the entire circumference of the LHC is 27 kilometers, but this alone, L times N, is 19 kilometers. So first realization we make is that in a machine like the LHC, and it's also true for the EIC and RIC and other colliders, is that the dipoles occupy 70% of the machine. So where do you think the cost of the machine comes from? Where is this $1 billion that I'm talking about? Well, it turns out it comes from making the dipoles. And that's how we can save by reusing the RIG magnets. We have, not 1,000 dipoles, but hundreds of dipoles in the machine. And each one of these dipoles, let's say it costs $3 million. So you multiply this number by 3, and you get that the cost of just the dipoles alone in the LHC tunnel is already close to $4 billion, plus the tunnel, plus the vacuum, plus helium, plus quadrupoles, and we as a community estimate that the LHC costed us $10 billion, of which $4 billion just for the dipoles. So it's a disproportionately high portion of the construction of a collider. And that's why if any of you is interested in the FCC-PP, you should be working on how to get the magnetic field higher. So let's calculate what is this magnetic field that we are talking about. How do we use this expression? V rho equal 2.3 times 10 to the 4 Tesla meters. Well, we use it like this. We know let's calculate the average radius of the band in LHC, and that's 19 divided by 19 times 10 to the 3 meters divided by 2 pi. Let's make it 6. So let's call it 3 times 10 to the 3 meters is the 3 kilometers is the average bending radius in LHC. And how do you now use this expression? I take 2.3 times 10 to the 4. So B then equals magnetic field in the dipole equals B rho divided by R. B rho is, by the way, it's 2 letters. That's what rigidity is. We just call it B rho. So 2.3 times 10 to the 4 Tesla meters divided by 3 times 10 to the 3 meter radius. That gives me roughly 8 Tesla. Voila. 8 Tesla is the state-of-the-art dipole magnet that LHC uses. People are working on 16 Tesla magnets, And it's going to take us 10 years to get there. The highest magnetic field that people built for MRI was in France just recently, 20 Tesla. A person went into its 20 Tesla field. I would never go there, but someone volunteered to go into a solenoid that was 20 Tesla solenoid. But that's a solenoid. And here we are talking about dipoles. What are those? Those are the dipoles, right? We started with the Tevatron. That's where all of the superconducting wire kind of came from in the world. That's where the MRI, resulted from producing in quantities wire that's called niobium titanium wire. Eventually, we built Hera. We built Rick. This is what I'm going to be. That's why it's so cost efficient for us to build this machine at Brookhaven, because we already have a bunch of those magnets. And finally, this is the most sophisticated dipole magnet that exists. It's really a beast, quite a big. It has two beams in the same magnet. It has various magnetic confinement and various mechanical structures because the magnet wants to blow up from Lorentz forces, right? So there are forces that are trying to push the magnet apart, magnetic forces. All of these elements here provide rigidity so that the magnet does not move when we cool it down to cryogenic temperature, because things shrink. First of all, when you cool them down, and then they want to they want to come apart when you apply electromagnetic fields. But so this is 8 Tesla, and in order to build the FCCHH at CERN, for example, we need at least 16, maybe 20. So many groups are actively working in the world on how to get to 20 Tesla. And I encourage you to start working. If you want to do physics, you should seriously think how to achieve high magnetic fields, because that's 70% of an accelerator, 19 divided by 27. That's where the cost is. That's why it takes us so long to build, is because someone had to build 1,500 of those puppies. 2 places in Europe, 2 companies built them, and then one by one, they were lowered underground by cranes and other, so installed in the. Any one of you have been to the LHC tunnel? Not yet? Okay. Next trip. 100 meters underground, very cool place. Make sure to wear your hard hat and steel toe shoes. Okay. So let's talk about now what do I have now. So let's go back to the table and then just so this is what I think I tried to first explain to you where these protons and electrons come from and what these energies mean. So 275 means superconducting magnets like this. Sorry, not such a good image. For some reason, I have a better image on my screen here, but it's a single pipe, a single beam pipe. Here it's 2 beam pipes in the same cryostat. Here, the Tevatron single beam pipe, both beams were circulating in one pipe, protons colliding with antiprotons. And Hera, of course, was an asymmetric collider, just like an AIC, similar. So the protons were circulating in the superconducting magnet, but electrons did not require such high magnetic field, so they were in separate copper magnet. Okay, so let's now talk about the luminosity finally. So the luminosity, which is really super important number for the entire machine. So that's the number that gives me the most headache, is how to get the luminosity to 10 to the 34. Of course, it's really easy to write down all the numbers so that you get 10.00 at the, for luminosity, but in reality, of course, this is a really difficult task, and so that by definition, the luminosity is simply the interaction rate per unit cross section. So if you know the cross section you are interested in, let's call it microbarn. You multiply the luminosity because it's in microbarn is a unit of area, so it's centimeters squared. You multiply luminosity by your favorite cross section, and you get the number of how many events how many of such events will be produced. It doesn't mean that you can detect it because someone else is going to talk how to detect it. The detection efficiency is super important, but I don't know. I mean, I am the one who is just producing these collisions. Someone else has to know how to actually detect the products of these collisions. But if you know the cross section, then the luminosity tells you how to get. So let me just go back and to this table and tell you how do I extract this number from this table. Okay, so it's a very trivial. I hope you are not bored, but this is helpful, I think. So let's go back. So the most trivial now I have to speed up, I guess. We're having fun, and then time is flying. Huh? Time is flying unless you're serving it. That's what they say. So so we have the luminosity that depends on the frequency of collisions of bunches. F is the frequency times number of particles in one bunch, number of particles in another bunch, divided by for Gaussian beam, 4 pi sigma x sigma y, where sigma is an RMS beam size, and then there is some factor F, which is always less than 1, and it has to do with various non-ideal conditions of collisions. For example, beams can collide at an angle, beams can be slightly different in size. So this assumes that the two beams are super short, delta function short, they have equal cross sections, and they collide without any offsets. So in general, there is some kind of a fudge factor that decreases this number, but this is an ideal number. And this fudge factor depends on things like something called an hourglass factor. That means that the beams are not quite, they get to the collision point from being too bigger and then small and then bigger again. So it's kind of a focus. So there are, that's called the hourglass factor, easy to calculate. Then there is Levinsky angle, that's an angle between collisions. So there are all these fudge factors but let's just ignore them for a moment and just look at this number and see how I arrive at this luminosity, 10 to the 34 centimeters squared per second. So let's start with a bunch with F. What's F? That's how often the beams collide in your detector, which is what? Huh? Well, it's we know that the EIC is going to be 3.8 kilometers long. Circumference is 3.8 kilometers. Okay, so we also know from here that the number of bunches is 1160. So the number of bunches is 1160. And then we also know that particles are moving with the speed of light. There is some, but we ignore that the beta is not 1. So F then is speed of light times the number of bunches divided by circumference. And that happens to be 0.92 times 10 to the 8 hertz. All right. So we are colliding with the speed, with the 800 megahertz. So the detector folks somewhere who is working on the detector for the IC. You guys should be, you better be ready because the collisions are going to be happening at 100 megahertz. Not, of course, not, they are producing a lot of garbage because the cross sections you are interested in are quite small. So but the biggest cross section is probably one barn. So there will be a lot of garbage produced, and you are looking for micro barn type or smaller events. So once in a while there is a nice, event that you're interested in, but there will be a lot of garbage produced at the rate of collisions, 100 megahertz. That's a huge rate. That can only be possible with modern electronics, modern AI, ML techniques that can look at this very intense data flow and sort out the garbage. It's like you are colliding two garbage cans and you're looking for, a lost ring in it. That's or a needle in, but really the garbage is flying everywhere because the typical cross section is one barn, but I think that the useful cross sections are less than a micro barn, much less maybe. I don't know. Julia, one micro barn or something? What is
I'm
that?
just trying to dig the information. Give me 1 second.
Okay, so that's the frequency. So then I look for my number of particles. Where do I find number of particles? Well, here it is 6.9 times 10 and 17.2. So let's write it all down. And notice that these are times 10 to the 10. So 6.9 times 17.2 times 10 to the 20, because both are in the units of 10 to the 10, divided by, let's call it 12. Then I'm looking for my RMS beam size at collision. IP means interaction point. IP RMS beam size, 95 and 8.5. So 95 microns, so 0.1 millimeter horizontally. One would ask me, if I were you, I would ask me, why did you make them flat? Why can't you make them smaller? Because look, the smaller beams here, the higher luminosity. Why did you end up with this number? Well, it turns out that electrons actually do not like to, the electrons radiate. They radiate, in the case of the electron collider, they radiate 10 megawatts of light. And by doing so, they produce something called quantum diffusion. It's quanta, radiation quanta is emitted not in a continuous manner, but in quantized manner. And when you do it, with the particle trajectory is jerked by the loss of this energy, and that creates a continuous diffusion in the horizontal plane. Therefore, naturally electron bunches are flat. And therefore, we have to match the proton bunches to be flat as well. And we match both beam sizes to match the electron beam size. So 9.5, 95, and 8.5 micrometers. So let's convert it to, so they're micrometers, so let's convert it to meters for now. So 10 to the minus 12 meters. And I want to, my units are by convention are centimeters, so I'm going to say that this is um, 10 to the, so I'm 10 to the 4 percent, so these are centimeters squared. And then my 0.92 times 10 to the 8 hertz, which is watts per second. And when I multiply this, all this together, I get 1.07 times 10 to the 34 per centimeter squared per second. Okay, slightly more than 1, but then there is a fudge factor, 0.94, which is the hourglass factor, which gives me, so if I multiply this by this fudge factor, hourglass effect, this gives me exactly 1.00 times 10 to the 34 per centimeter squared per second. And that's how I fulfill my DOE 4 little lines. Remember I showed to you that asked me to deliver 10 to 34 per centimeter, yes.
And now the question to the students. So the minimum bias cross section, so like DIS, neutral current, 65 microbarn.
Okay. So the cross section we are interested in, or someone interested in,
65, take 100
or
microbarn.
this is a neutral current.
Yes.
Let's call it 100
microbarn.
microbarn.
Yes. And let's calculate the number of events we collect in a year with this luminosity. So this is like all events, which,
So-
you know.
But I think, am I correct that, I mean, a typical nuclear cross section of any, like is 1 bar? I mean, I think that there are,
It's, this is neutral current.
no, I understand, but I mean,
Yeah,
but
DIS.
But this is an interesting event. Non-interesting event is
There will
could be
be
as big
many-
as 1 bar.
Yes, yeah.
Okay,
But
so
this is what
so that's
like-
why.
Neutral
Okay.
current.
So with 1 bar converted to a normal to meter squared or centimeter squared. Anyone can convert 1 bar to a.
So the boson-gluon fusion, where you produce CC bar pairs, the cross section is 16 nanobarns. Charge current is 100 picobarns, and the leptoquark production is 1 femtobarn. So now you can create a table and see how many events you will get and what will be the garbage.
Okay.
This is homework fish.
Well. So. We'll do it for you. So 100 times 10 to the minus 6. Huh? Someone tell me what. Remember, we like Gaussian units. Right? Is that the right number? Am I,
24.
huh?
Minus 24?
Minus 20.
Yes.
He wants centimeters.
Yeah, centimeters squared, that's wrong.
So that's 10 to the minus 28 or 10 centimeter squared. So my event rate, the rate then is L times sigma neutral current. And then that's 10 to the 34 times 10 to the minus 28 equals 10 to the 6 per second. So at the rate of 1 megahertz, you're going to be producing neutral current events. And right? And so you better be ready because there is also 1 million more events that are not interesting, but this one is interesting, and you're going to be producing it at the rate of 1 million per second in AIC. And we'll have to sort through 1 million times more stuff non-interesting to you because that's what's been already studied. But that's how this works. The efficiency of the detector after you calculate, of course, may be only 1%. I don't know, because you don't cover the full solid angle, you don't cover, you can't quite catch everyone, you cannot reconstruct it, but it may be 1% or less. I don't know what the efficiency is, but sometimes in the Tevatron we had efficiencies of 10⁻⁴. So we work hard to produce these events with accelerators, and then the detector, downgrades the rate by a large number. But, okay, are we good here? Does anyone understand what this number luminosity means now? Okay. I've lost. Okay, so let's go on. I am actually running out of time, so I'm going to try to talk about focusing now. Remember my three simple recipes to build an accelerator. One is you need particles. We know where particles come from. We accelerate, using either type of a battery or radio frequency fields. We bend using dipole fields, and now we need to understand how one can. What the heck is happened anyway? So in order to understand how to bend particles or to focus particles, we use a simple approximation that is also called a paraxial approximation. That's a word that only means that the trajectories of particles are near axis. That's what that means, paraxial. And so why is this approximation interesting? Well, let me see what's on my next slide. So here's an example of optical elements without bending. So here you start with the cathode at the transmission electron microscope, or I forgot what S stands for, but so you have various lenses, you have a specimen, then more lenses, and then detectors. So this is a system of optical elements that focus the electron beam from an electron microscope to your detector. That's the simplest electrostatic type machine that uses this technique. So the idea of this paraxial optics, of course, this is the most simplified description in accelerator that I can give you. Comes from the fact that if the transverse momenta are small, much smaller than 1, typically they are of the order of 10⁻⁴. This is an RMS type, 10⁻⁴. If this is the case, then you can simplify the equations of motion by replacing d over dt with v naught times d over ds, where s is the coordinate, longitudinal coordinate along the beam trajectory. That's I think it's a very common simplification. So instead of talking about solving the equation of motion in the time domain, you solve the equation for trajectories. It's a ray tracing, but essentially it becomes ray tracing rather than the actual solution of a, equation of motion. By assuming that the velocity of a particle does not change while it's traversing, typically it's the speed of light, it's just c for relativistic beams. This assumption allows for us to use many of the mathematical apparatus that has been developed for regular optics, including the so-called matrix formalism. For example, if the particle is in a drift space, so between dipoles, let's say it's in a drift space, then of course in this drift space you have no forces, right? So there are no fields in a drift space. Therefore, but by replacing this with the paraxial equation, I actually get d2r over ds squared equals 0. And we know that this solution can be approximated by a drift space matrix using two initial conditions. So that, let's say, x and x prime equals this transverse angle of a particle, theta. Also, we're calling it x prime by convention. So this is theta, p, transverse momentum over full. So then at the distance, some distance down the drift line, this is simply, you need to do a matrix multiplication of so that's a typical optical transport formalism in which you are using either 2x2 or 4x4 matrices with unit determinants in order to describe your transport system. So you can also come up with a matrix for thin lenses. This is a simple formalism. You should remember it from your E&M classes or from optics. But so because it's a paraxial approximation, I can switch from solving equations of motion in the time domain to describing the trajectory by ray tracing it, essentially. So in order to focus the beam, we use, so we've talked about already dipoles, right? For the LHC, we said that the LHC dipoles have 8 Tesla magnetic field in them. We use them to bend particles. So we bend, then there is a drift. We bend again, then there is a drift. So this is, 70% of the LHC orbit is occupied by dipoles to bend the beam in the circle. And 30% by some kind of drifts or focusing elements, which are quadrupoles. So the quadrupoles are very commonly used in accelerators in order to focus the beam. Why? How does the focusing, by the way, there are quite a few focusing elements that exist. I showed to you already an example from an electron microscope, which uses some kind of condenser lenses, projection lens, those are electrostatic pancake type lenses. I'm not going to talk about this because they are low energy, non-interesting stuff. This technology that has been in existence for, 50 years already. what I can give you before we before we finish today is an example of how this works for quadrupoles. So for a quadrupole, let's say that we have a quadrupole that's has a cross section like this. I'm gonna have four poles like this with four-way symmetry. South pole, north pole here. So the field at the center is 0. It has to satisfy the Laplace equation. Not the field, the magnetostatic potential. Let's call this distance A, like here. That's the radius. I'm going to call it diameter to be A. Oh, no, 2A. 2A, like this. So I'm going to, just to remind to you that the field in the gap here, dx equals minus g times y, and by minus g times x, where g is the gradient measured in Gauss per centimeter. So the field here, let's say, is 0 at the center. Here, the field is some kind of B. Then the gradient is B over A. So if you have a quadrupole magnet with the field, but at the pole, let's say in LHC, we talk about the field at the pole of 5 Tesla. And the size of the beam pipe is 10 centimeters. So the radius is 5 centimeters divided by 5 centimeters. Then we are talking about G equals 1 Tesla per centimeter. That's a very high field, but it's needed for very high energy particles in LHC. So this is my fields. So now, of course, I have to remember my standard equation of motion. It's a V cross B. And after I linearize this, after I plug in this type of fields for quadrupole, I arrive at a very simple expression that x double prime minus 1 second. Okay. X double prime equals EG over gamma beta MC squared times x equals 0. And then for the vertical motion, so times y. So you can see that within the quadrupole, so notice that even though the signs here are equal, but because of the cross product, the sign changes, right? So you can notice for here that the expression E over gamma beta MC squared is beam rigidity. Therefore, this expression can be actually written as x double prime minus g over b rho for beam x equals 0. and y plus g over b rho y equals 0. So these are trivial equations, of course, nothing, but these are linearized equations of motion that in one case resemble a harmonic oscillator. So if you leave if the gradient, if this quadrupole is infinitely long, you will see that this particle will start oscillating. The trajectory will be a sine wave, or sine of combination of sine and cosine, and this will be the solution here. Hyperbolic cosine and sine. So this expression, this trajectory diverges. So this is how quadruples work by. And by the way, the solution, of course, for if the quadrupole has a finite length, then within this length, you have to solve this equation. So the quadrupole has a finite length L. Then within the quadrupole, the equation of motion is given by this simple harmonic oscillator. Outside of the quadrupole, it's a drift. So we have to remember this, and if we want to, then the solution of this simple harmonic oscillator again can be expressed through a matrix equation. Let me see where I have. So here is the solution for. We commonly call this. We often call this number. This expression. Just we call it K. And the solution of this is given by a matrix, again, with determinant equal to 1. As you can see, sorry for, I think when my file was copied, things shifted from one computer to another. Okay, so the trajectory, therefore, if I take a combination of drifts and matrices like this, my entire accelerator can be represented by the product of these various matrices. So for the entire machine, I have a common equation of motion that is nothing more than some kind of a time, some kind of an oscillator with a time-dependent force, which in the simplest case, K can be positive, 0, or negative. And the solution of my trajectory then is a product of these matrices that correspond to various elements in the machine. So I start from right to left. Remember, we start with the initial conditions. And then if my first element in the machine is a drift, I multiply this by a matrix that corresponds to a drift. We call it L1. Followed by a quadrupole, let's say focusing quadrupole, that would have some cosine here, cosine. Then there is another drift. Then there will be another quadrupole that's now defocusing, and so on. And then you go in circle to construct the entire matrix transfer for the entire accelerator, whether it's LHC or RIC or the EIC, just remembering that this K, the coefficient, has a periodic structure. Where C is the circumference of the machine. So how does this work? I'm finishing up. So here, for example, is the structure. By convention, we use focusing elements to show the horizontal degree of freedom. So that would correspond to focusing in the horizontal degree of freedom. And so a typical structure then is called the FODO. Focus, drift, defocus. It's funny how we call drift, but we actually designated them all. And this is how it works then. The beam is passing through a series of quadruples. Each one focuses in one plane and defocuses in another. But if you stack them one after another, you can see how passing through a series of focusing, defocusing elements in one plane and correspondingly defocusing, focusing, defocusing, focusing in another plane keeps the beam still stable. The beam remains confined because you have a series of lenses that change sign from one to an opposite in both planes symmetrically, even though, of course, the sequence is different. Okay, so now this is how the accelerators work. And therefore, all of the synchrotrons that we use this type of periodic focusing systems. But just to let you know that the equation like this can be solved for an arbitrary K. It has a very long academic history. You know, Noether's theorem goes back to finding. So this is actually an integrable equation for an arbitrary K. And it has a very long history and it has many applications. So it's an oscillator with a time-dependent force, solvable and integrable in for any type of smooth function K, and not smooth also. Okay, so I'm finishing up. And I will have to tell my friend Christoph that he needs to introduce the emittance, and because I didn't get to the discussion about this number emittance. So I guess we will stop for now. There will be something tomorrow more that they'll catch up for questions for me.
We'll have a discussion this evening, and I've converted the PowerPoint into PDF to put that on. Is there any urgent questions at the moment? We can. Okay, you can think about it. We'll discuss it more, but thanks, Sergey, again. So.
When do we come back?
145 is out. 145, would that work?
145.
145 is that? Yeah, a little bit longer. So, yeah. 175.